Light, the very essence of our vision, is made of particles called photons. These tiny packets of energy are fundamental to how we perceive the universe. But here's the fascinating part. A photon at rest has no mass. Imagine that, a particle with no inherent weight. This weightlessness is crucial because it allows photons to travel at the fastest speed possible, the speed of light. If photons had mass, they would be like sluggish space travelers, never reaching the incredible speeds they are known for. Their lack of mass is what allows them to zip across the cosmos, carrying information about distant stars and galaxies. This concept of a massless particle might seem strange, but it's a fundamental principle of modern physics. It's what allows light to behave as both a wave and a particle, a duality that has puzzled scientists for centuries. Understanding this duality is key to unlocking the secrets of the universe, from the smallest subatomic particles to the largest cosmic structures. But wait, there's a twist. While a photon at rest has no mass, a photon in motion does possess a kind of effective mass. This might seem counterintuitive, but it's a consequence of Einstein's famous equation, E equals mx squared. This equation tells us that energy and mass are intimately related, like two sides of the same cosmic coin. When a photon is moving, it carries energy. And because energy and mass are linked, that moving photon also behaves as if it has mass. The faster the photon moves, the more energy it carries and the greater its effective mass becomes. It's like a cosmic dance, where energy transforms into a kind of mass, giving the photon momentum as it travels through space. This effective mass is not the same as the rest mass of a particle like an electron or a proton. Those particles have an inherent mass, even when they are not moving. But for a photon, its mass is entirely dependent on its motion. It's a fascinating example of how energy and motion can give rise to properties we normally associate with mass. Now, how do we actually calculate the mass of a moving photon? Well, we can rearrange Einstein's equation to solve for mass m equals E over c squared. This tells us that the mass of a photon is equal to its energy divided by the speed of light squared. Let's break this down. The energy of a photon is determined by its frequency, or color. Higher frequency photons, like those in blue light, carry more energy than lower frequency photons like those in red light. The speed of light is a constant, approximately 299,792,458 meters per second. So, to calculate the mass of a photon, we simply divide its energy, determined by its frequency, by the speed of light squared. This gives us a tiny, tiny number, but it's not zero. It's a testament to the mind-bending nature of relativity, where energy and mass are intertwined in a cosmic dance. Section 4. Counting the messengers of light. But how do we determine the number of photons in a beam of light? It seems like an impossible task, counting particles that travel at the speed of light. However, scientists have developed clever methods to do just that. One way is to use a device called a photomultiplier tube. This ingenious device works by converting the energy of individual photons into measurable electrical signals. By counting these signals, we can determine the number of photons hitting the detector. Another method involves using the photoelectric effect, where light shining on a metal surface can knock electrons loose. By measuring the current of these ejected electrons, we can infer the number of photons striking the metal. These techniques, and others like them, allow us to study light not just as a wave, but also as a stream of individual particles. It's like having a cosmic counter, allowing us to probe the quantum nature of light and unlock its secrets. Section 5. The weight of a sunbeam. While the mass of a single photon is incredibly small, the total mass of all the photons in a beam of light can be significant, especially when we consider the vast scales of the cosmos. For example, the sunlight that bathes our planet carries an enormous amount of energy. If we could somehow weigh a sunbeam, we would find that it has a surprisingly large mass. This mass is constantly bombarding Earth, transferring energy that drives our weather patterns, powers photosynthesis, and sustains life as we know it. The concept of light carrying mass has profound implications for our understanding of the universe. It affects everything from the evolution of stars to the behavior of black holes. It's a testament to the interconnectedness of energy, mass, and motion in the fabric of space-time. So the next time you see a beam of light, remember that it's not just illuminating our world, it's also carrying a tiny bit of weight, a cosmic reminder of the profound mysteries that the universe holds.